I am Pavel and I'm here to explain the solution for problem E delivery service. In this problem, we are given a delivery network over 200,000 cities and we want to hire 400,000 couriers, 400,000 couriers who would deliver our packages. So each of them would live in one city, and each morning he would pick up required packages and go to some other city, fix it for this person, and go back in the evening. So, for example, if we have one person who is going from city 1 to city 2 each morning and back each evening, and another person who is going from city 3 to city 2 each morning and back each evening, we can deliver packages from 1 to 3 by them going with this package in the morning to city 2, meeting the other delivery person, and going from city 2 to city 3 back in the evening. So after hiring each new delivery person, we need to say how much cities are connected in both ways, so we can deliver both packages from A to B and from B to A. To make further formulas simpler, let's simplify it. Let's simplify the value we need to compute a bit. Now we need to compute a number of pairs A and B that are different and don't depend on the order, for which we can deliver from A to B. But as we mentioned, we can see that it easily can be seen that that if we can deliver from A to B, then we can also deliver from B to A, so order actually doesn't matter. So we can just compute both and divide by 2 in the end. To make it even more simpler, we can also say that we can deliver from A to A, and then we would just need to subtract n. So instead of computing what we asked, we would compute a number of pairs AB without any restrictions, so we can go from A to B, and that fix it right in the end. To do this, we would split each of our vertices in 2 vertices corresponding to day and night in this city. So if we have someone who goes from 1 to 2 each morning and back each evening, we would draw an edge from city 1 in the night to city 2 in the day, and vice versa. What we can do is we can deliver any package within any connected component of this new graph. The problem is, if we just compute number of pairs in this graph, we would compute some things twice. Because, for example, if we can deliver from night in city 1 to both night and day in city 2, we would count this twice, while we need to count it only once. But this is easy case. If this is in one component, we can just ignore vertices, the second copy of vertex in the same component. So the problem happens when we have edges, when we have pairs such that we can deliver from day to night. For example, we can deliver from day to night in the other city, and also from night to day, but we cannot deliver between day and day. Then we would count it twice in different components, which we need to fix. So, how to count the overall number of such pairs? For each component, we can compute the total number of different vertices in this component, and the total number of pairs would be just sum of A squared over all components. But what we counted twice? We counted, so for each vertex, we can compute a pair x and y of the components it is located in. And if some vertices have the same value of this pair and order it, then we compute it twice and need to subtract it. So for each of such pair, we can compute the list of vertices which has this pair of components right now. And in the end, let's call it C, and in the end we need to subtract sum of C squared over all pairs. That would be our answer. This already gives us quadratic solution, which is too slow for current constraints. To optimize it, we need to use a small to large merging techniques. What is it? So let's, for each component and for each pair of components, compute not just a number of such vertices, but just a list of them. We can, whenever we want to merge some components because new delivery person appeared and the new edges in our graph appeared and some components emerged, we just go through the smaller of the lists and put all elements from it to another list. This can be done in time of size of this smaller graph. Smaller component multiplied by data structures we need, which is probably logarithmic or of 1, depending on whether it's map or an ordered map or something else. This would lead each vertex move to some other place logarithmic number of times, because each time we move something, it moved to a component which is at least twice bigger, because we go through the smaller component. This means that overall time of our solution would be n log n multiplied by our data structure, which is again either logarithmic or constant. Both should be good enough. That's it.